of our meeting today. She is Elena Aladova from University of São Paulo, and she will speak about automorphisms of the category of free associative algebras. Please, Elena.
Please begin.
And for me, my main motivation for studying automorphisms is to come from universal algebraic geometry. I have no time to speak about this area, but just for information. The next reason why it is important to study automorphisms is the general physics. It's very important for the algebraic variant, and if we have every time some object, it's interesting to study objects. It's interesting to study the group of automorphism of this object. A little bit about what is category. Let K be a field. Now it's an arbitrary field. And K of x1, xn is a free linear algebra. It may be, now it's not important, now it may be commutative, now commutative, associative, not associative, just a linear algebra. And in general, category have two parts. It's object of the category and morphism of the category. And objects of our main category is a category C. It's a category of free linear algebras. Objects of this category are free finitely generated linear algebras. I will write in this form if we need to generate this x1, xn, or in more short form if it's not important all which generators we have. Important the set of generators. The set of generators x. And morphisms in this category just a homomorphism of three algebras. If we speak about category, we also speak about composition of morphisms. And in this case, composition is just a composition of homomorphisms as a function. So our main object is this category of objects, free finitely generated non-associative algebras with unit, and morphisms are homomorphisms of this algebra. The group of the big O of the morphisms have two important subgroups. We can divide the group to the group of inner automorphisms. This subgroup is normal, and the group of so-called strongest. I also will give definition of this. That definition of this subgroup, how we understand that. In general, the name inner. It comes from the group theory. We know that we have an inner automorphism group. The idea of construct this automorphism of the category is the same. We get new morphisms by conjugation. By conjugation, they are automorphisms. The group of strongly stable automorphisms have the same structure. They also have conjugations, but not the elements, formally not by elements of this category. What we know about all groups, we know that this group is a product of the group of inner automorphisms and a group of strongly stable automorphisms. And for a linear algebra, this unit, we have a lot of specified the first value for distinguish in this group, in the group of strongly stable automorphisms, we can distinguish a special subgroup of. I will also say that this group of strongly stable, I can do it for the new name for this, but just for attention. C means, for instance, this group, I cannot say that this group And for here also, we can simplify the process further, and we can say that the group of all automorphisms is also a product of a group of inner automorphisms, which is normal for group, and these special subgroups. In this subgroup allows us to simplify population. We will study the group of stories. Because normally the construction of group of inner automorphisms is more or less clear. The main problem to study a group of all automorphisms is to find a group of strongly stable automorphisms. And so for us, the main problem is strongly stable. And for this, we use the method of verbal operation. What is the factor of Aristotle and the origin? Then, after he removed this method, he introduced this notion because paper there is no and what we have? We have one-to-one correspondence between strongly stable automorphisms and so-called verbal operations on our free algebra. And a little bit what about verbal operations? So let K be an algebra free non-associative weak unit, F1, Fn, some elements of the algebra, and we can take some word B. It can be word C, also some element of the algebra, but with different variables. And we can say that operation omega B, an array operation, because we take the power of k of x to k, it's an array operation, and this operation defined by the rule. We apply result of applying operation omega b to elements f1, fn is exactly the value of this word under these elements. So we have this word, it's some element of x of algebra k of x, and this is by definition, it's called verbal operation on the algebra k of x, defined by this word v. This word exactly as a result of applying this array operation. Each operation we have on our algebra, linear algebra k of x. Usually, if we speak about linear algebra, we assume that it has three operations. Plus, binary operation, multiplication by a scalar, I'll use it like this, and just multiplication. But I need more logical, more model theoretical, more formal fields. And really, linear algebra has more operations. First of all, linear algebra with unit have two non-array operation. Non-array operation of constant, it's 0 and 1. They have two types of unary operation. They have unary operation minus. For each element f, it's a minus f. And generally, it's have a collection of unary operation by multiplication by a scalar, because each scalar defines a new multiplication. So it's not one operation, it's just a collection, depends on our field. If our field is finite, it means that we have a finite number of operations, but it's infinite, we have an infinite set of unary operations. And two binary operations, just plus as usual and multiplication. scalar unary operations, and plus and dot is binary operations. So formally we have says operations. And for trivial example, just as a verb operation, the original operations are defined by these words as a verbal operation. So we have a minus as a minus x, multiplication by a scalar defined by the word alpha x, or defined by the polynomial alpha x, plus defined by the word x1 plus x2, and dot defined multiplication defined by the word x1, x2. Or trivial example, so we could, for example, we have defined unary operation minus by in new way using this word. V of x1 is because we define unary operation, use only one word. We need to use word with one variable. So just take V of x1 as a x1 plus beta x1 to the power 2. Beta some scalar. We can define new operation minus. And getting new algebraic structure. Formally, yes, we have a set with some operations and we get some universal algebra. Of course, there it's not already linear algebra, but it's an algebra. The main question is when. So the question is when this algebra is defines all operations by a new way. When this algebra is a linear algebra. It's really one of the main problems and one of the main questions in this method. But in general, how this method works. So, I said already that what one corresponds is always stable automorphisms. Here I already speak about this group and verbal operations. But what does it mean? It means that for each, if we have a strongly stable automorphism, we have a free linear algebra with new operations. I denote this algebra by k of x w, where w is a set of words. Which defines a new operation. So the operation minus defined by the word b minus of x1. New multiplication by a scalar defined by the word b alpha of x1. It's unary operation, so they defined by the word with one variables. With one variable. Sum and product, use sum product defined by the words v plus and v dot. It should be worked with formally, but not more than two variables. So formally we can define binary operation by working with one variable. It's possible, but it's not. It should be not more than two variables. Now, first of all, we need that this algebra is a free linear algebra. Original algebra. But what is important is not we need any algebra. We need any isomorphism. We need isomorphism which preserve generators, which the set x should the variable x should become to x next. So formally we can construct some isomorphism which not but if we need correspondingly strongly stable automorphisms, it should be free. This new algebra should be free in an algebra which is isomorphic to the original one with this special isomorphism. So the main problem to find strongly stable automorphism is to find all algebras of this type. If we know all these algebras, we know all strongly stable algebras. And from now on, K is an infinite field because I will speak about results and proof, and in this case we use that K is an infinite field. So, because workshop about combinatorics, and the main idea of Natal is to speak about a little bit about proof, because the proof is purely combinatorial. So we have the first step. First step is to find a system of words, to find all words of this in this system, such that new algebra is a linear algebra. What we use. The example explain in general how we work with board. We don't with multiplication because it's more with two variables and it's more simple than the operation of the sum. So, as an element of the free linear non-associative algebra, this word can be written really in various forms. For example, for associative algebras, we just can read as a sum of powers of monomials, but if algebra is not associative, it's more complicated to write in more clear form. But for non-associative algebras, for example, we can present polynomial as a sum of monomials as a sum of homogeneous polynomials. So each polynomial has the same degree. So P0 isn't just an element of a field because we work with algebra with unit. P1 is a sum of polynomials of degree 1, P2 all polynomials of degree 2, and so on. But for our proof, it's more convenient to use another representation. We present this mode in this way. We use R element and three polynomials f of x1, g of x2, and h of x1 x2, where f of x1 and g of x1 are polynomial without constant terms, and depending only x1 and x2 respectively. And h of x1 x2 is also polynomial without constant terms, but because each polynomial contains both variables, x1 and x2. And what we have. And we start, we know that if we would like that our algebra is a linear algebra, it should satisfy some identities. First of all, we try to use most simple identities which we have. So our original algebra, K of x, satisfies the following two identities. X product of x and 0 is 0 and x is 0. It means that new operational multiplication should also satisfy these identities. 0, h of x 0. The same with other identities. And it should be this polynomial is a 0 polynomial. And this implies that R0 should be 0. And h of x0, h of 0y, x1 and h0, x2 should be 0, also by construction of h, because it contains both, all monomials with both variables, x and y, x1 and x2. Plus, it implies that f of x1 and g of x2 it should be also 0 polynomial. And we get that our original equation, we have this equation, and we get that h, a1, a0, f, and g, they are 0 polynomials. So we have some restrictions on our word. We have the operation. If b dot, if the word b dot define the operation of multiplication of our new algebra, it should be of this form. So we need to be simplifying the word. The next step, we can use these identities. I use one as a just not as a multiplication by x scalar, I use one as an element of algebra. So algebra units satisfy these two identities. It means that new algebra should satisfy these two identities. And in particular, it implies that x should be h of x1 and x should be h of 1x. This means that because h is a non-associative polynomial, this is some special field. This means that h of x1 should be of 1 with respect to x and by construction. But it means that for a non-associative algebra, we have this polynomial h of x1 is the polynomial of this form. It's alpha 1 to xy minus alpha 2 y. So alpha 1 to alpha 2 1 some element of the field. But then we have this also this identity in this form that multiplication by 1 implies that x is this polynomial. And in particular, it means that alpha 1 to alpha to 1 not an element, they should satisfy this equation. So sum of these two elements should be 1. So but in addition, if we assume that our new operation is commutative, this implies this fact, and this fact implies that they should be equal. So since we speak about non-commutative, non-associative algebras, so our new multiplication can be defined by this form: v dot equal alpha 1 to x1 x2 alpha 2 1 x2 x1, where alpha 1 2 doesn't equal alpha 2 1, and sum of them is equal 1. So we have already we have a very small word, it's not the regional word. With this word, we already continue to work. But really, this word is really defined the new operation or linear algebra. So really, it's the final step for. There are no other reduction. About other words, I will not move about other words, but if we need to find the word, to find multiplication by a scalar, we should to take some polynomial which depends on alpha, with one variable. If we need to define words which define new sum, we should work with two variables, and we also use the same representation as a multiplication. And we get these two words also 0, but with h there are more work. We have more work. But for this we also use simple identities for linear algebra. So, and at the end we get the system of words W of this form minus f p of alpha x1 x plus x1 plus x2 and this polynomial. This system of words can define new linear algebra. Here, phi is automorphism, so really we can change the deformation of only two operations. We can make deformation of the operation by a scalar multiplication. The other operation the same. Now I did say that because I choose the special subgroup and the group of strongly stable automorphisms, it allows to translate 0 to 0. It allows to assume that our set of our constants are the same. 0 comes to 0 and 1 comes to 1. So this system of words may define new linear algebra. And this is really not only linear algebra. Since of x is a PI-algebra, we can define homomorphism between PI-algebra and some algebra in the linear algebra. So it's just a universal property. But and we can define homomorphism which preserves generators. And there it's a proof. It's not clear. It's some proof. And really, this automorphism is not just a homomorphism. This homomorphism is a isomorphism. So this new algebra is a really free linear algebra which satisfies some additional property, which is amorphic. The original one, but with some special kind of isomorphism. And just the last point to find this group. So we define a set. We know the set of strongly stable automorphisms, but we need also the structure of the group as a group. And so just some notation before we will speak about structure of this group. Let G be a group of 2 by 2 matrices of a field K of this form. It's a very special form. They are equal by they have this matrix. They have the same elements of the main diagonal and other diagonal, such that the alpha 1 2 does not equal alpha 2 1, and the sum of these elements is 1. can define the action of the group of automorphism of the field on this group by this way. So what is the action? It's just that there are various definitions, but I will say about the action as a map for the power of the group of automorphism and G2G, such that for each one we put this matrix, where this matrix we denote by a few objects, and the semi-direct product of G and out K is a group, with this multiplication. So it's a semi-direct product is a group defined on the set of the set of pi. First element of the group G, the second element of the group of automorphism, with two specific multiplication. So we multiply G1 by, not by G2 as a direct product, by some conjugation, some new element which depends on P1, we make some difference. And the second element is just a composition of automorphism. And then the group of strongly stable automorphisms is isomorphic to the semi-direct product of the group G, it's the group of matrix specific, and the group of all automorphisms. The second main step in this research is to study the group of outer automorphisms, because really the group of outer automorphisms play important role in universal geometry, and in some sense this group measure for us some difference between two geometrical equivalence of algebras. But this group of outer automorphisms is a measure for us differences between two types of equivalences. And in the case of algebraic unit, we get that the group of outer automorphisms is isomorphic also to this group, because we get the intersection of group of inner automorphisms and this specific subgroup is trivial in all cases. So we consider the case of nonassociative. It's only for nonassociative algebras, but we already have results for some subclasses which admits unit. So Jordan algebras, alternative power associative homomorphic commutative. So our Lie algebras are not with unit. So but subclasses of algebras with unit, but it's really they kind of the same, but the general idea that this subgroup trivial intersection with a group of inner automorphisms. So it's more simplified. It's more simple to study the group of outer automorphisms. So that's all. Thank you.
Okay, thank you, Elena. If someone has some comments or questions, please.
Questions, comments, please. Viviane, we got the question here. We got to transmit. The question is from our room here. We are here. Arkady, please come and make a question. Yes, it's turned like this. Viviane, tell us if you can hear us. Yeah, go ahead.
Two questions. This result is published? Published?
This result was sent to publications.
And
Subvariety signature. It's just already in progress to set.
And about this group, G, maybe this group is isomorphic to the group of all invertible elements of the field. Okay. In my paper, there is this idea.
I tried, but no,
Louder, please. Speak louder.
no, it's not because if we speak about field, this group does not contain covariant half, because about 2, alpha 1, 2 does not equal alpha 2, 1, and some of it should be 1. So it's not a multiplication. I also think about this group in the sum, in the other form, but it's not with multiplication of the field. It's not a group. It's not this group. It's maybe we have other group, but I don't know. It's
Okay.
maybe more specialist in the group theory. No.
Specialist in the field. Thank you.
Okay.
Yeah, maybe we have more questions from our audience. Yeah. We pass to our digital part of event. Please, Viviane.
Okay. Okay, then let us thank the speaker again.
Just thank the speaker. Thank you, Elena. Thank you for your time.
Okay, our next talk will be on 4 minutes.
Yeah, Viviane, we have at least, we will need some technical minutes, some break. We are here. When we are ready, I'll let you know. Maybe it's going to be 10 minutes. Anyway, after we figure out with the sound, let's figure out with sound during this technical break. Maybe I even start.
Okay, then maybe 10 minutes.
Yeah, we have the time. Trust me, we have the time.
Yeah,
We're gonna be all right.
Okay, maybe we can try the sound